Okay, part 3, just to check where we are. We had a timber roof beam, which looks like that. 6 meter span. It has a load of dead load, snow load, and wind acting upwards, which we're not considering at the moment. We have gone through the load limit states of 1.35 is dead load, 1.2 times the dead, and 1.5 times the snow load. And we found that that second one is the limit state that we're going to find for. That's the strength limit state. We have picked an F11 seasoned timber beam, and we've worked out a basic size on that based on a 60 millimeter deflection. And so we've ended up with 45 by 240 size beam. Now, it's also worth mentioning that you should check this against ratios. For a regular timber beam, you should be looking at a span to depth ratio of 15 to 25. So if I got 6,000 millimeter span, if I divide that by 15, that's 400. If I divide that by 25, that's about 240. So I should be looking at a beam somewhere between 240 millimeters deep and 400 millimeters deep. Now, I am right at the upper limit of this. So this is towards the more slender end of where you should be. The reason I'm at the upper limit is we've got a fairly lightly loaded roof. We've got a whole lot of beams in parallel, so they're not heavily loaded. If this was a beam, say, under here, which was supporting a whole lot of these beams, you'd expect to be more towards the lower end. Just so you know, when you're in steel, you should be looking at ratios of between about 25, span to 25, and to span on 40. Sometimes span on 50 if you really push it limits. So, but these are your typical ratios for timber, which is what we have. So we'll go to page 3 now, and we're going to work out first the strength. We're going to work out the strength of this beam in bending. So we come to our page here, and we know that CSU example. We know that MD, which is the capacity bending moment of our beam, equals phi times K1, K4, K6, K9, K12, F-B times Z. Okay, and that comes from AS 1170 clause 3.2. Alright, if we're back in the code, that's that formula right there. Alright, so we need to go through and find out all these. Now we know from page 1, M star, that's our load, is 10.02, and we'll get that from page 1. So in this right hand column, I'm writing all the code references. Also, if I pull some result from an early page, I'll say where I got it from, just so someone who's following the calculations and checking them knows where we're up to. Alright, let's work through these factors one at a time. Phi, if we go to a phi factor, comes from table 2.1. So open our code to table 2.1. And table 2.1, value of capacity factor for calculating design capacity of structural members. So this is bending and axial force and that kind of thing, and this is the joints down here. So we're up in this table. Stress grades, MGP 15, no. All other timber grades, here we are. So category 1, structural members of houses which failure will be unlikely to affect an area of greater than 25 square meters. Now we know that this beam was 6 meters long and it's every 900 mil. So if we go 0.9 times 6 meters, if one of these beams failed, it will bring down about 5.5 square meters of roof. So that's less than 25 meters. It's also a secondary member it is in a house, so that doesn't count. So we're looking for a value of 0.9. Okay, so phi equals 0.9, and that comes from table 2.1. Alright, let's look at our K1 factor. Our K1 factor comes from table 2.3. There's table 2.3, and we know that snow in a non-alpine area, if you read in this list on this side, is 5 days. So we're going to take a factor of 0.94. 0.94 for snow. While we're here, because we're going to come back later and do the uplift, we know that the uplift is a 5-second duration, so it's 1.0 for uplift. And that's table 2.3. Now I should point out at this time that we remember back on page 1 we had the moment for the dead load only was 2.73, and the moment for live load and dead load was 10.02. For the permanent load only, the K factor is 0.57. So if that was anywhere near that, I would be going and checking to see which one of those is more severe. Now, if that was anything above 6, you should be checking that. I know in this case that because that is way more than that, this is still going to govern, so I'm not going to go any further. Okay, that's K1. Let's do K4. K4 is the partial seasoning factor. And when we're using seasoned timber, K4, for seasoned timber, K4 generally equals 1. It's only otherwise when we're in a very damp environment where the timber is actually going to get wet and unseason itself. So that's clause 2.4.2.3. K4. Alright, next one is K6. K6 is the temperature factor. Is this thing in North Queensland or not? No, it's not. It's in orange, so that's 1.0. And that comes from clause 2.4.3. So we've done those. Now up to the K9 factor. Obvious joke about dogs. Alright, K9 factor is a strength sharing factor. Basically, is this beam on its own, or can it share strength with others? And to do the K9 factor, you look at the section here in the clause 2.4.5, and to get to the K9, you need a thing called NCOM and NMEM. Alright? So, now in this case, NCOM equals 1.0, or 1 really. How many of these beams are together? None of them nailed together. It's an individual beam. NCOM equals 1. NMEM, which is the number of members acting in parallel, which says, alright, how many of these beams are there lined up across this roof? Now, to be fair, I haven't told you that. I've just said there's a large number of beams. Now the table maxes out at 10, so we'll take 10 or more. So we'll go 10 plus. Okay, now, so then I need a factor for G31 and G32. Okay, so G31 and G32. I go to table 2.7. NCOM is 1, G31 is 1.0. G31 equals 1.0, and that's from table 2.7. And to get G32, I have to multiply NCOM times NMEM, so it's 1 times 10. 1 times 10 obviously is 10, so G32 is 1.33. G32 equals 1.33. Now we have to go to this equation here. K9 equals G31 plus G32 minus G31, all multiplied by 1 minus 2s over L, but not less than 1, and that is clause 2.4.5.3. So we also need S and L. S is the center to center spacing of the discrete parallel members. So that's 900 millimeters. And L is the effective span, which is 6,000 millimeters. Okay. When I put all that into an equation, I get 1 plus 1.33 minus 1 multiplied by 1 minus 2 times 900 over 6,000. And that all equals 0.769. Okay? But K9 cannot be less than 1. Okay, therefore K9 equals 1.0. Alright, K9 equals 1.0. We'll highlight that as well. Alright, let's go on to page 4. The next one after K9 is a K12. Okay, here's where the real fun starts. K12 is the slenderness factor, and it's basically a bit like the lateral torsional buckling. So we need to know about the slenderness ratio. So the first thing to do in K12 is K12 comes from clause 3.2.4 of the code, and which says if rho b times S1 is less than 10, then K12 is 1. If rho b times S1 is between 10 and 20, there's a formula. If it's over the 20, there's another formula. Alright, so we need to first find what's rho b. Rho b comes from table 3.1. So if we go over to table 3.1, material constant rho b for sawn timber beams. There we are, F11, seasoned timber 0.98. Alright, rho b equals 0.98, and that's table 3.1. Good. And the S, which is slenderness ratio. Our slenderness ratio then is all about the restraints this has. Now you recall that I said this is restrained by these battens at 900 millimeters. So those are 900 mil apart. So these are top restraints to this beam, which is most like that picture there. We've got the load applied to the top of the beam from the roof. We have the factors, these restraints, these are 900 mil apart, so LAY is 900, and the discrete restraints are applied to the compression edge. Now notice it's going to be different in the uplift case with the wind, where the restraints are on the tension edge, so you get a different formula. But in this case, the formula for that is over here, 1.25 times d over b, lay over d to the power of 0.5. Alright, there's the formula right there on this sheet. So S1 equals 1.25 times d over b times lay over d to the power of 0.5. Which is now our d over b. Our d is the depth of the beam, which is 240. Our b is 45 millimeters. All right, and our lay equals 900 millimeters. So we've got all the different bits. Let's put it together now. So 1.25 times d, which is 240, over b, which is 45. Times lay, which is 900, over d, which is 240, all to the power of 0.5. Put that into the magic box here. Aren't you glad you aren't using slide rule these days? (900) 240. Okay, and I get 12.9. Alright, so our rho b, that's our S1, so our rho b S1 equals that, remember it was 0.98. So rho b S1 is that times 0.98, which is 12.65, and 12.65 is between 10 and 20. So rho b is between 10 and 20, so our K12 is that there. Our K12 equals 1.5 minus 0.05 times rho b S2, SZ, which equals 1.5 minus 0.05 times 12.65. And that 12.65.05 times that equals 0.867. So K12 equals 0.867, and that's all from clause 3.2.3 in the code. So basically, the K12 is telling us that we can use 86.7% of the full bending capacity in this case because the beam's a little bit slender. All right, let's come back for part 5.